Good day, sir. We are to present to you our critique analysis on a study about performance comparison of reactive power control methods of photovoltaic microinverter. So for the introduction, renewable energies, particularly solar, are an interesting and growing alternative electricity generation source in recent years. Solar power is abundant, renewable, and pollution-free. It is most commonly available in the midst of increased natural energy interest. Several types of inverter circuits and the corresponding control systems have been studied for PV systems. The interactive PV systems with a grid can be categorized into following three sorts: are the central inverter, string inverter, and AC module system. The AC module strategy has been suggested in this paper to overcome the drawback of other types of PV inverter, including high-tension DC cables, power loss associated with central MPPT, loss mismatch between solar AC modules, and loss mismatch between photovoltaic modules and inverter. AC module system with ranging of low power levels of microinverter is used in this paper. There are many advantages of AC module, includes 1. Improve the energy harvesting. 2. Improved efficiency of the system. Third, lower cost of installation. Next, operation, plug and play. 5. Increased modularity and flexibility. And lastly, enable the capacitance of DC capacitor. This paper presented two photovoltaic system of three-phase grid-connected microinverter with two design methods of control of reactive power. The first design method proposed that the system is using a DC to DC boost converter in the DC to DC conversion stage and pulse width modulation voltage source inverter, or the VSI. Control of reactive power is achieved by regulating the Q component of inverter current in the D to Q reference frame of three-phase inverter currents. The second designed by using interleaved flyback converter on a stage of DC to DC converter, and the third harmonic current injection current or circuit for reactive power control with a current source inverter, or the CSI. The output power provides into the utility grid varies over time. When the power is taken from the photovoltaic panel, needs to be fixed value to improve power harvesting. That causes a mismatch between instantaneous input power and the instantaneous output power. So components of energy storage have to be located between the input and the output of balancing instantaneous input power and instantaneous output power.
Summary. This study, entitled Performance Comparison of Reactive Power Control Methods of Photovoltaic Microinverter, a critique paper. This paper will study the performance comparison of two photovoltaic systems of three-phase grid-connected microinverter and study their design methods of reactive power control. The feasibility of the program is demonstrated by the MATLAB software simulation. The performance comparison contributed to achieve a nearly sinusoidal output current, a reactive power control injected into the grid, high efficiency, more reliability, reduction in THD, reduction in DC link capacitance value. Photovoltaic power generation becomes an important technology in recent years because of its advantages such as clean energy, pollution reduction, no gas emissions, maintenance and operation requirements are low. So, it is a new path for generating electric power. The first design is suggested that the photovoltaic systems based on an interleaved DC to DC boost type converter with its maximum power point tracking control, or MPPT, for each boost converter, a voltage source inverter type, or VSI, is used as a three-phase microinverter by controlling the direct and quadrature components of inverter output currents. Reactive power controlling is achieved at 90.76% efficiency. The second design is suggested that the photovoltaic panel is connected to DC converter of an interleaved flyback type. Each subconverter is controlled by an individual MPPT. The circuit of active third harmonic current injection in recent years have received much interest. This technique contributed to get better quality of current injected into the utility grid and to control the power with good efficiency at 95.07%. A line commutate current source inverter or CSI with filter is used. The developed microinverter of 1000 watts offers an expanded range of reactive power control with balanced three-phase output power. Each system design in this study has proven its effectiveness in obtaining control over reactive power and nearly sinusoidal three-phase output currents.
Critical evaluation. Power control system means system or devices which electronically limit or control steady-state currents to a programmable limit, improve process performance, and save on energy cost with our formidable range of power products. Covering all types of load and voltage, these reliable products offer features such as high performance alarm strategies and advanced diagnostic load fault detection and are supported by our vast experience in all types of power control applications. With this, it is related to performance comparison of reactive power control methods of photovoltaic microinverter. The study utilizes different kinds of controller to generate electric power and to develop microinverter of 1000 watts. Control of reactive power is achieved by regulating the Q component of inverter current in a D to Q reference frame of three-phase inverter currents. The second design by using interleaved by flyback converter in a stage of DC to DC converter, and the third harmonic current injection circuit for active power control with current source inverter or CSI. The output power provides into the utility grid varies over time. When the power is taken from the photovoltaic panel needs to be fixed value to improve power harvesting. That causes a mismatch between instantaneous input power and the instantaneous output power. So components of energy storage have to be located between the input and the output for balancing instantaneous input power and instantaneous output power. And the conclusion, the design of control of reactive power for a three-phase microinverter is described by taking two system design with different methods. In the first system design, the converter is composed of the interleaved DC to DC boost converter. A VSI is used as an integrated microconverter with a sinusoidal PWM strategy. Power control of the associated boost converter such as DC voltage regulator and current controller allows injecting a three-phase current with desired reactive power control to the grid. In the second system design, a secondary topology concept of a PV system, which presented the capability of control of reactive power for three-phase microinverter grid connected. For interleaved flyback converter are used in the DC-DC converter stage. The third harmonic injection circuit is used for controlling third harmonic injection current, hence an expected power factor correction is achieved. A line commutated CSI inverter is designed for converting the direct current from a flyback converter to a three-phase output currents that can be injected into the grid. The microinverter can be operated with full power level of 1000 watts. This proposed system is suitable for AC module PV system application, and the microinverter has the ability to inject active and reactive power into the grid.